Hello everyone. I hope you all had a nice refreshing tea or coffee. So we will start with the second session of track 1 on day 1. Let me introduce you to our speakers. Ranjan K. Sahoo. I'd like to request both the speakers to please come on the stage so that the audience can see you. Please come. So Ranjan K. Sahoo is working as Technical Director at NXP Bangalore. He is responsible for the high-speed I/O IP design for the advanced analog business line of NXP Semiconductor and drives the overall roadmap, strategy, business, and technology. Prior to joining NXP Semiconductor, he worked with Intel Technologies for almost 15 years, both in circuit and system aspects of IP design for various protocols like DDR, HBM/IO, PCI Gen 1 to Gen 6, and USB 3 and USB 4. He has exposure to every aspect of IP design, including but not limited to circuit design, system architecture, signal and power integrity, with multiple successful tape-outs and product cycles across various process nodes. His areas of interest are feasibility study and architecture definition, system-level performance, analysis, and algorithm to optimize the SERDES performance. He holds a master's degree in microelectronics and VLSI design from IIT Madras. Thank you, Ranjan, for joining us. Our second speaker is Sriram Kanduri, who is working as principal engineer at NXP Bangalore. He is responsible for the HSIO SERDES system design and modeling at NXP Semiconductors. Prior to joining NXP Semiconductor, he has worked with Broadcom, Cypress, Infineon, and Qualcomm for almost 10 years on physical layer WLAN systems engineering. He worked on 802.11 BE AX AC GNN standards and has experience in systems engineering, modeling, firmware, FPGA bring-up, design verification, pre-silicon, and post-silicon chip bring-up. His areas of interest are wired and wireless communication system design, signal processing algorithms, and he holds a master's degree from communication and signal processing from IIT Madras. Thank you for joining us. And we would like to start the session with the first part of the session that will be done by Ranjan, and it will be followed by Sriram. And on a personal note, Ranjan and I go a long way. We have worked together for 15 plus years, and it has been an absolute honor to learn from him. I'm looking forward to this session as much as all of you are. Thank you.
Good morning to all of you. Thank you, Gaurav, for the warm welcome and nice introduction. I would like to thank the entire organized committee for giving me this opportunity, and I hope to do justice to the privilege given. So let's quickly go over the outlines. So these are the few topics we will be discussing today. We'll start with a quick overview. Gaurav, can this slide be a little dimmed? Yeah. We'll start with a brief overview of SERDES and HSIO link. Then what are the associated challenges we deal with when we design high-speed IOs? And probably there are many challenges. We'll pick one of the challenges, that is ISI cancellation through equalization. We'll talk more about this today's session. And then link performance parameters and how to optimize them, various analysis methods, and then we'll take a particular architecture and see how do we kind of analyze and kind of a case study, and then briefly present the results and key takeaways or summaries basically. So let's start with the overview. So before we talk about high-speed links or SERDES systems, let's look at how a processor system looks like. So if you look like a processor system, will have a processor and a co-processor or chipset control. For the server platform, there could be many processors like this and a host of peripheral devices connected. So host of peripheral devices could be internally in the platform or could be external also, like our USB chips and all so on. So let's, in the plus, there could be processor to processor interfaces, which is kind of taken care by OPI, DMI and UCI, and there are some custom interfaces also by various companies. Similarly, processor to memory, so that's basically DDR, HBM, and they are parallel interface. When I say parallel, there will be basically clock, data and address buses, and the rest of the peripherals which I am outlining is processor to other peripherals will be predominantly HSIO serial interfaces. So, they are PCI buses, USB, DP, HDMI, and PCI primarily between the components in the platform, whereas USB could be external, USB, DP and HDMI external, and various storage protocols like SATA, UFS, PCI, USB also nowadays kind of used for the storage protocols, and Ethernet is predominantly for all the network requirements. That is the various protocols. So, now let us look at the data growth rate in last 1.5 decade. So, if you look at in 2010 time frame, the data was around few zettabytes. Today we are talking about 175 zettabytes. Look at the absolute number, which is like definitely huge. Look at the rate of the growth, it's almost exponential. Every year the growth rate is like 20-30%. So, to meet this demand, processor compute power of course has to increase, no doubt about that. The data rate, the data transfer rate between the components also has to increase. Let us start looking at the PCI, how they have evolved over the years. So, in 90s, PCI started with if I remember correctly 33 megahertz with a 32-bit parallel interface, and eventually they converted that to a 2.5 Gbps serial link in 2003, and thereafter look at the growth rate. Today we are talking about PCI Gen 6, which is 64 Gbps, a Palm 4 interface, and I think they are on track for this year release of PCI Gen 7 spec, which is 128 Gbps. Started with 33 megahertz in 90s. Today we are talking about 128 Gbps. That is the growth story of PCI to meet this demand. USB is not far behind. So, they started with 12 Mbps in 90s. Today we are talking about 80 Gbps USB links. USB, though like if you look at bulk of the market, we are talking about USB 3, 4, but for servers and all, USB 4, 40 Gbps on track, and USB 4 version 2, which is 80 Gbps for accelerator and other things. Look at the Ethernet story. Ethernet started with again 10 Gbps in 80s, and today we are talking about 400 gigabit Ethernet, and in 2030 it is expected to meet 3.2 terabit per second. This is the growth story of Ethernet, and thanks to all of you, all of us rather, for the large amount of internet data, and that's the, and the most interesting part with this growth rate also, this is not enough. It's kind of a dil mange more story. This is truly not enough. If we can give more, industry is ready to consume that. And Ethernet story is slightly different. They kind of combine multiple lanes to form the link, high Gbps. If you look at 100 Gbps, so basically that could be 25 into 4 links or 10 Gbps into 10 links and so on. Okay. So, for a link to be established, there are various layers in the communication. So, our focus will be mostly today in the physical, So, this is where our focus will be, physical layer, And in physical layer also there are two aspects of it. One is basically the logic layer and other one is the electrical layer. So our focus primarily will be to the electrical sublayer and how to optimize it, how to look at the link performance, all those things we will be discussing today. So let's look at how a typical HSIO links look like. Probably it's we serialize the data and send the data in a differential link to the other side of the device, and we have a termination, and probably if there is no channel loss, it is a very straightforward affair. We send the data, we receive the data and sample the data at the middle of the eye, and we are done with it basically. So then even today we will not be talking about this, it is just like a inverter to inverter communication. So let's look at the challenges. When we talk about the challenges, we will talk about more, but before that, let's look at the different type of clocking architecture possible in this scenario. So we can have a common clock which is sitting in the center and providing clock to both the link, that's called common clock. And the other one is basically we can forward the clock along with the data, that is called source synchronous system, so that your clock and data traverse together, there is no mismatch, you sample the data successfully. The next one is embedded clock. In this case we do not send the clock at all, data is toggling and data is basically sampled from the TX clock here, and it has the clock information, we can recover the clock from the data and sample it. So that's basically last part, embedded clock. So this is most of the SERDES, if not all, most of the SERDES fall into this category basically. This is called a presynchronous system. So let's look at what are the challenges we face. Okay. So if this communication, irrespective of speed, Dr. Professor in the previous session talked about 100 gigahertz and all those things. If it is inverter to inverter communication, then there is no problem at all. We just put two inverters next to each other and then send the data, receive the data. But in this particular case, if you see here, the transmitter device will be sitting somewhere in this daughter card, and that data has to traverse on the daughter card, and then again the back plane, and then again another daughter card and a device somewhere here. So when this data travels from this point to the other side, few things will happen. One is basically the insertion loss itself due to the RC nature of this material. Then there will be change in materials, vias and all, there will be mismatch and reflections, and there could be crosstalks also. So basically when you have two adjacent lanes kind of routed together like Bangalore traffic jam basically, so there will be crosstalk between adjacent signals also. So when one signal is toggling, the adjacent signal is also toggling in the opposite direction. If they are toggling in the same direction, probably okay. If they are toggling in the opposite direction, that will create a crosstalk or the droop in the voltage. So that also will create a problem. Due to these three problems, the signal whatever we sent from the transmitter side was wide open in terms of voltage, but when it reaches the receiver, it's completely closed basically. So we have no signal I basically. So what are the So we talked about ISI crosstalk. On top of it, own device. This device will have intrinsic noise and jitters also. So we talked about this channel ISI, mismatch reflections, crosstalks, and intrinsic noise and jitters. This together makes the system really complex. So what eventually happens, when we started with a circuit problem, we thought this is just a circuit design from one device to other. It becomes a kind of system challenge where we need to have expert in circuit. We need to have expertise in communication system where we talk about the bit error rate, the SNR, all those things. And also we will see in the subsequent foils we need adaptive equalization also. That's why the expertise in DSP also come into picture. And the most importantly, how do we analyze all this? It's basically from all the way transmitter till the receiver, every component, every aspect or every anomalies must be modeled accurately, and the budget should be allocated, and how much margin we have should be predicted accurately. That is the challenge basically, and most of the things will be talking. So these are the questions must be answered, because it's now you can see three distinct systems. One is the transmitter sitting on one data board, we have the receiver, and then we have the channel. So three components. So the transmitter spec must be defined carefully, how much swing and equalization scheme we should have, how much insertion loss we can tolerate, how much crosstalk mismatch reflection we can tolerate. Then having these two defined clearly, how our receiver should look like, whether we should have one gain stage, two gain stage, one equalization, one type of equalization, multiple type of equalization, what kind of receiver we'll have, and also what should be the intrinsic and residual error in intrinsic noise jitter and the residual errors from the receivers. And of course, on top of it, process and voltage temperature variation makes it worse. If process probably you can calibrate initially, but if voltage temperature is huge, then you have to have some kind of adaptive equalization, which we will talk about that. Okay, so let's talk about the challenge number 1, which is inter-symbol interference. I think there is some. Okay, so let's look at here. If we have very less channel loss, for as an example, I have taken only 2 dB. So it looks like a CMOS signal. You can just see it is reaching the rail. There is no ISI. I is wide open. So now let's increase the channel loss a little bit. Remember, this is basically only channel loss component is taken, no other non-additive is included. So if I just increase the channel loss, what happens? Look at the I is almost like say 70% closed. Let's increase little bit. I is complete closed now. So you can see this area, probably I have a marker there. Look at this where I am kind of circled. So this was supposed to be a 1, it is kind of effectively will be detected as a 0 basically. This is kind of bit error, and this is the problem inter-symbol interference or the channel loss brings to the table, which needs to be addressed. And a point to be noted here is ISI creates both voltage noise, which is seen here, of course I is closed with voltage noise, and look at this horizontal axis also, it creates a time jitter also. So ISI creates both voltage noise as well as time jitter. Okay, so let's see what is the source of this ISI due to insertion loss. I am sure most of you or all of you must be familiar with this RC circuit. So, and we also know a RC circuit takes almost 5 time constant to reach the steady state voltage, which is basically this is the steady state voltage. It needs 5 time constant to reach 99%. Of course, t is equal to infinity, it takes infinite time to reach steady state, but 5 time constant where it reaches almost 99%, 99.99% basically. So now we can do 2 things. We can keep increasing the switching frequency, charging discharging frequency we can increase, or keep this frequency constant, increase the R and C, impact will be same. So if we increase the frequency, problem will be that it is not fully charged, we are trying to discharge, and if you are keeping the frequency same but increasing the R and C, impacts also will be same. So now by definition, when we call a high speed, we are dealing with a high speed link is this. When we do not have 5 time constant of the RC circuit or the platform we are dealing with, if our time period is much less than 5 time constants, we will have problem of ISI. So irrespective of data rate, it is both the channel insertion loss and the data rate together will decide whether we are dealing with a high speed link or a low speed link. When you have, so now what happens, basically this is what we have already seen. So basically if you have a low frequency pattern, it finds time to fully charge, and if you have a high speed pattern, it does not find time to fully charge and you are starting discharging, and there will be places where it will not cross even the threshold voltage or the midpoint where you can slice the. So this is the basically problem ISA brings to the table, and I would like to some discussion happening. Okay, so let's look at little more in details. So let's say we have two pulses, 1, 0, 1 basically. We are trying to transmit 1, 0, 1, and by let's say if one pulse have a response something like this green one, the next pulse also will have exactly same behavior because this time invariant system we are assuming. Now the resultant waveform by principle of superposition is the red one basically. And now we can see this when the 0 was supposed to be transmitted, this particular voltage couldn't go to 0 basically. Why it couldn't go to 0? Basically two problems, and I want to introduce two terminologies basically, a precursor and a postcursor. So basically what you can see, this green one has some impact on the blue one, means the previous bit has the impact of the next bit. So at this point this much residual is still there from the previous bit, and at this point another thing you can see, when this is trying to discharge, the next bit started coming this. So basically impact of this on the past bit is called precursor, and impact of this the next bit is called postcursor. So these are the terminologies which I will be using in the next slides. That's why I wanted to kind of have that outlined here. The next challenge is basically dealing with the noise itself. So let's look at what problem noise brings in. So if we have a signal which is that blue rectangular waveform plus minus 100 millivolt, if there is no noise, probably we don't have any problem to sample the signal. We put a comparator at 100 millivolt and sample the signal. Now if we have noise, let's look at what problem it brings in. So you can see now, if this is, I just for simplicity I have taken a Gaussian noise and see the PDF of this Gaussian noise, and in this area you can see both have reached almost 0, but let's zoom in that area to kind of highlight the focus, highlight the problem. So if I zoom in there, so there is a point you can see when this red line crosses this blue line somewhere here. So what does it say? So if you look at this red shaded area, that is the probability of 0 being detected as 1, because if this, of course it's a very low probability, but it is non-zero probability. So it has a, this particular voltage due to noise will be detected as 1. Probability that 0 will be detected as 1. And now let's look at the bottom one, that is the probability 1 will be detected as 0, and together give you the total probability of bit error rate. 1 will be detected as 0 or 0 will be detected as 1, both gives you bit error rate. So that's the problem we'll face due to noise. Similar, of course, this is intuitive, higher the noise, higher the probability of bit error rates, and this two shaded area gives us the total probability, which I already outlined. So now, okay, few assumptions I made, so that's fine. So, we will have predominantly two types of noise. One is basically the random Gaussian noise, which is due to the device physics, thermal precurrent short noise, and that is statistical in nature. And it's difficult to find out the peak to peak value, but we can find out the total power, and from that we can find out the sigma, and all the time mean will be 0 basically. And how much will be the peak to peak? It will be a function of number of bits we transmit. If we transmit let's say very less number of bits, the peak to peak also will be less. If we try to transmit 10 to the power 12 or 10 to the power 15 bits, that number will keep increasing. This is unbounded. That is how it is characterized. The next one is deterministic, or probably we can kind of calculate how much will be the peak to peak value, which comes due to power supply noise, channel loss and ISI we talked about, and then offset, residual offset and mismatch reflection, all those things are deterministic. Another one which is also deterministic, crosstalk due to aggressor on the victim, but I have deliberately categorized the third category, that's bounded but uncorrelated. Though it's a deterministic noise, but it's uncorrelated. Basically, you do not know when your neighbor will toggle. That amplitude is fixed, but the timing is unpredictable. That's an uncorrelated noise, and it creates an uncorrelated jitter. So that needs to be treated differently. Okay, so third challenge is jitter. Let's look at that. Here I have considered zero noise. It's a pure rectangular basically waveform, and same thing. Basically, I have taken the distribution of this noise here. This is jitter axis, and our area of interest is this, where they are crossing each other, and what is the probability of that. Same thing. So there is a finite probability, though low probability, but there is a finite probability when bit slip will happen. There we said 1 will be detected as 0 or 0 will be detected as 1. Here we will be sampling, or in other words there will be a timing violation, we will be sampling the previous or next bit. So here in this case, if you see there is a finite probability, we will be sampling the next bit. Of course that's an error. And this side will be sampling the previous bit. Instead of sampling the present bit, we will be sampling the next bit or the previous bit. So that's the problem statement the jitter brings to the table, and it's basically same problem but in a different domain basically. There it was in a voltage domain, here the problem is in the time domain. The concept remains almost same. Another key takeaway here is they are not completely uncorrelated. It's not that voltage is another aspect and time is another aspect, you treat them separately, they are not. They are very much correlated. Not all, but most of them are correlated. Noise basically creates jitter. But there are some noise, some jitter which is, for example, duty cycle has no relation with the voltage noise. So few things are correlated, few are uncorrelated. That aspect also has to be kept in mind while analyzing. And this probably exactly same thing what we discussed with 3 components, random and deterministic, and then deterministic uncorrelated. I'll just skip through this. Okay, the fourth challenge is crosstalk and reflection. So crosstalk and reflection, if we see, so let's say we are basically dealing with this particular path, this transmitter to this receiver we are dealing with, and in this particular system let's say we have 2 transmitters and 1 receiver. So this red line is a desired path, transmission is happening through the metal track, but when this transmitter is toggling, transmitter 1 is toggling, that will have some impact on this. So that basically called far end crosstalk. This far end transmitter toggling, that is having an impact on this particular receiver. That's far end crosstalk. Then there is a near end crosstalk when this particular transmitter is toggling, and that also will have some impact on this. That's called near end crosstalk. And then reflection is basically when this particular signal is traveling, if it is a single medium and uniform, there is no mismatch, then there will be smooth transfer of the data. But if there is a medium change or there is a VRs, impedance mismatches, then this particular signal will reflect back. Let us say for example 95% pass through, 5% reflects back, and then that will come to the other side, again it will reflect back. So this is called reflection. So if I plot that signal, basically the red one is basically your main signal, and then there will be some amount of crosstalk and reflection. Reflection I have not plotted here, but there will be FEXT or far end crosstalk and near end crosstalk. And if you look at most of on-tie coupling will be capacitive in nature, and most of package or platform there will be both capacitive and inductive coupling. So that needs to be kind of carefully designed. Okay, just to kind of summarize what we talked so far. So now we talked about this voltage noise and their distribution, both the side, and similarly there is time noise and their distribution. I had a Gaussian distribution in the previous file because I had assumed that noise is Gaussian, but that's not the case. If you have both deterministic and Gaussian noise, so then this distribution could be something like this, bimodal. This is the deterministic component, peak to peak, and there will be a Gaussian tail basically, which we saw basically. So now if we look at this region, assume that we have known what we assumed in the previous file, your VREF has no noise and your clock has no jitter. If we have noise on this VREF signal and we have jitter on this clock sampling, look at the effective eye height is further reducing. So which was this much from this center to top of this eye, now it is further reducing and only this much is available basically. Similarly, eye width also, if you have clock jitter, that will further reduce your eye width also. This eye height margin, this is eye width margin. So this is kind of outlined what we talked about. Your eye height margin depends on the noise and offset on the data signal as well as on the offset and noise on the VREF signal. So on this VREF signal basically. And similarly, your eye width margin depends on the data jitter, of course, which you saw, and as well as clock jitter. If clock is not clean, that also will create some additional eye loss. And they are not completely independent, which we already talked about. Your eye height and eye width, they are not completely independent of each other. Okay, so these are the challenges we talked about. Insertion loss and the associated ISI problem we talked about, noise and jitter we talked about, crosstalk, and these are the few mitigations outlined. Insertion loss and ISI is taken care by equalization. Noise and jitter, of course, better power supply. All these things is beyond the scope of today's discussion, but we will be discussing insertion loss and ISI problem and how do we kind of deal with that. So rest of the files will be discussing on this equalization techniques. Okay, so let's look at. Okay, before we talk about anything, first we should know what is the data rate we are talking about and what is the insertion loss and what is the bit error rate target and the modulation schemes and how much spec we can allocate to transmitter, how much insertion loss can be allocated to the medium and how much receiver has to do the heavy lifting. That's the question must be answered before we. And once we have those things, then we should see how many stages of receiver we have, 1 stage, 2 stage, how much is the minimum and maximum gain, because think of a situation, if it is a fixed platform where you have kind of inside server both the components are placed, probably you know that channel insertion loss not going to change. Let us think of a USB thing. When someone will connect through a 1 meter cable and another person will connect that through a 1 feet cable or just a USB stick for example, your insertion loss is dynamically varying. Means you need to have enough gain if you have a long channel or high loss medium to adapt that, and also a very low loss also it has to adapt to that. Means your receiver has to work if you have a long channel as well as short channel. Okay, so then all the equalization, let us say you have now example I am saying 28 dB loss channel or 23 dB loss channel. So now all the equalization responsibility is on the receiver, or TX can take some of the burden basically. If TX can take some of the burden, that also needs to be planned. How much voltage and temperature drift you need to budget? It's only 10% or 20% or 30%. That also have say on your design or architecture. And what kind of clocking you want to have? How much is the jitter spec on those clocking and architectures? So those are the key questions we will try to answer in the next of the sessions. Okay. So if you look at, if we just have the PCB, it's a RC in nature, you will have a basically, as you increase the frequency, your loss will be high, your signal strength will deteriorate. And due to the crosstalk and reflection, you can see it is, you see some kind of notches also. So this will be the frequency domain behavior of your signal. Higher the frequency, lesser the amplitude. Now, if we can have some receiver circuit which will just behave oppositely, like for example, for the low frequency you will have lower gain and for high frequency you will have higher gain. Just opposite behavior of this green signal. Then probably we can cancel the effect of, and you will have a flat gain for the signal. This is what we want theoretically, and this is called precisely the equalization. The equalization means irrespective of frequency of a signal, whether it is a clock pattern 1010 pattern or you have a DC pattern, let us say 16 bit 1, 16 bit 0 pattern, your signal strength should remain same. When you are sampling the signal, you are sampling the same signal. That is called equalization. And we will talk about how to take care of these notches and all. So there are other techniques, but broadly this is equalization. You have RC behavior and you are just mimicking the opposite behavior of that, and you are equalizing the signal irrespective of the frequency. And this is the time domain presentation. You can see the blue one is frequency signal is very high. You can see its amplitude is decreasing, and if it is DC in nature, amplitude is high, and by equalization you are making almost same, and you can see the notches here. We are doing the opposite of this also. Whatever your channel is treating the signal with reflection crosstalks, that also taken care here through DFE. We will talk about that also. So this is a time domain view of equalization, this is a frequency domain view of the equalization. So if kind of I demonstrated correctly, can I say increase the gain at the high frequency basically. So that's we call equalization. Next question then, whether it's a analog filter, is it of course a high pass filter which is evident, whether it's an analog or digital filter. Implementation specific, there is no one rule it has to be analog or digital filter, it's implementation specific. Different people will have different implementation. Where the filter to be placed? Only in receiver, only in transmitter, or both? That also protocol specific. Some protocol allows in both the places, some protocol only in one place, all those things we will see. What are the filter parameters? Like 2-tap filter, 3-tap filter, 1-tap filter, or even multi-tap filters? One time adaptive, or we can make it continuously adaptive. Static or adaptive, I am saying. Static means one time you can just fix the coefficients and be done with it, or you continuously adapt. So, how to take care of the PBT variations, how to take care of noise, jitter and crosstalk, which we saw some of it basically. Reflection, residual errors, all these things needs to be addressed when we are designing the circuit. So, let us look at how a typical circuit, remember this is just to demonstrate the idea, this is not kind of has to be this way basically. If we look at a SERDES link or HSIO link, if you will have a transmitter where we will have control for swing as well as equalization, then of course the channel specification, how much loss maximum loss we can have and minimum loss we can have, and then these are the few components. One equalization circuit, this is the analog continuous time linear equalizer, this analog filter is placed, then you will have gain stages, and then this is again a digital filter. So, if you look at here, what is happening, we are discretizing the data, this is the slicer which is making the analog data to digital, and we are taking this digital data, multiplying a coefficient with that and subtracting from the incoming signal. Means, if you remember we were talking about precursor, post-cursor definitions. So, if we know there is some impact due to the past bits or previous bits basically, we subtract that much, let us say there was a 20% or 30% residual error from the past bit, we subtract 30% of the signal from the previous bit and remove that basically. This is again a digital filter, a analog filter for equalization, and of course some gain stages. And the most important component is sitting here, the CDR clock. It recovers the clock and tries to sample the data at appropriate positions. So, if we look at this, what exactly we try to do, we set the two reference voltages, positive and negative, and we, irrespective of data pattern, we try to make sure this always the swing is between these two layers. Whether it's this, I think we saw in the previous timing diagram also, irrespective of frequency, this just touches these two VREF level. And we have basically 4 areas of operation where we can say if this swing is more than this, we call error is 1 and error is 0 here, and we take this error into account to do the required correction. That is why we are calling it error basically, and we have more files on that to demonstrate that. So, in this case, if we see we have swing control from TX and equalization, CDR of course we talked about, VGA is for gain and CTL EDFE for the equalization. CTL is an analog filter and DFE is a digital filter. So, this is my one line answer for equalization, irrespective of frequency of the data, swing at sampler is always plus minus VREF. That is the theoretical requirement is this, irrespective of the frequency of the data, my swing will be always between these 2 points. Okay. And this is kind of a very high level steps needed to achieve the target. So, first thing is basically if you have any DC offset, remove them. The next you allow CDR to lock to the incoming data. If CDR is not locked, you will be sampling all over the places and it has no meaning basically. So, you allow CDR to lock to the incoming data to make sense of the data. Then adjust the gain to meet the swing target. In this case, we are calling VREF at the slicer input, and then engage the equalization circuits to minimize the spread. We saw this due to the ISI swing, it was spread all across. So, basically you make sure to address that voltage spread around VREF and timing spread also around zero crossing. And the last one is basically all the protocol does not allow that. If protocol allows, you adjust the far end transmitter swing and equalization also, so that you will have better margin. Okay, so let's quickly spend few minutes on CDR, each blocks before we talk about the system level. So in CDR, what we do, we know the data frequency. First, we use the loop 1 basic, this particular loop, coarse loop, and tune to the known frequency of operation, and then basically the bottom loop does the frequency locking, and the top one is basically phase locking. So once you know the frequency, let's say for 10 Gbps your VCO is operating at 5 GHz, I am just giving an example. Then you first calibrate this through your bottom loop to particular required frequency 5 GHz, and then when data starts coming at 5 GHz and its harmonics, you track the phase. This is tracking, this is the initial calibration and frequency locking. And your objective is basically sample the data at this particular position where your eye is wide open. So I talked about this. Let's go to the next one. A popular, I've just captured one phase detector which is most popular in SERDES. It's a Alexander Bang Bang phase detector. So what is done there is basically you take two consecutive samples and one edge sample, and you find out the phase based on the edge value. You take two data samples and one edge sample. Whenever there is a toggle, you look at that. Probably this next picture will be make it clear. So let's look at this. So we talked about two data. Basically, this is data 1 and this is data 2, and the middle one is basically edge. It was supposed to be sample on the edge, and you can see it is little late. That's why we are calling it clock. In this particular case, clock is late, and I can say data is early. And next one, if you see, there is a toggle 110, and this particular one was supposed to be here, but it is little early. So its clock is early basically. So with two data samples and one edge samples, and if there is a toggle, you can predict whether my clock is early or late. And this is the truth table given for that. And this is a possible implementation of this truth table. And if there is no, if you look at A and C, in this case is the data and B is edge. If 1 0 or 1 0 1, then only you are making a decision. All other combinations, basically there will be 8 combinations, only 4 are considered here. All other combinations, you do not have any phase information. So you hold that, don't make any movements basically. So few important parameters for the CDR. Of course, the phase noise itself, which is coming from the device itself, has to be taken care through proper topology and then device sizes. Other one is basically your power supply noise. Again, this power integrity, better power supply, differential topology, all those things. The third one, probably important parameters, that is coming from the CDR itself. So kind of loop latency you have, loop parameters Kp, Ka and KVCO, and the step size itself will decide what is called a dithering noise. So when you are tracking the incoming frequency, so if these parameters are not optimized, either will overshoot or undershoot. So this has to be kind of managed carefully. And this one is basically, if you see, if you want to have a better tracking, this parameter needs to be high basically. Kp, Ka, KVCO has to be high. That comes with if you make them high, then there is a dithering noise will be more basically. You will probability of overshooting and undershooting will be more. So your requirement is conflicting if you see. You need a higher Kp, Ka, KVCO to have a faster tracking, and faster tracking leads to higher overshoot and undershoot. That has to be carefully balanced. This is probably most important factor in CDR design. So all these things needs to be carefully optimized so that your dithering jitter is within control. Okay, so now let's move to the next block, is basically a gain control. So this probably the most simplest block. If there is no ISI, let's look at what we do. We basically increase the gain to get the increased eye height. So it is very intuitive. You increase the gain, you increase the signal. So there is no problem whatsoever. Now let's look at this scenario. So we have a signal laced with ISI. So now I increase the gain. So there was a problem of ISI and I increased the gain of the signal thinking that my eye will open up, but to my surprise there is not much benefit. What exactly happened? So there is no benefit at all. I double the gain, hardly any improvement in my eye. So what exactly happened? So as we increase the gain, we amplified both signal as well as noise. So we amplified the signal as well as the ISI noise. So benefit is almost nil. So your SNR is maintained basically. Now what is the solution? Unless we cancel this ISI, your VGA or gain will have no significant benefit. To cancel this ISI, of course, increasing gain will give you a better eye height. So the point I am trying to highlight is, yes, you can control the gain to increase the swing and all those things, but if you are not cancelling the ISI, all these things is of no use. So now let's qualitatively look at the equalization before we go into any circuit implementations. So let's look at, if I just included a continuous time linear equalizer, you can see this, which was a DC got attenuated and AC got amplified. You can see here AC got amplified and DC got attenuated just by CTLE. Now I just deployed another circuit called DFE and you can see the impact. Here look at the residual ISI and here you look at the residual ISI. Now again I added TXFFE. There are some more benefit. So now question is whether I should have only CTLE or CTLE plus DFE or all three, or even some more circuits which I have not included. The point is, depends on your data rate, how much SNR you are targeting, what is the bit array rate and all those things. Depending, you have to see what is the solution space we are looking for. We will discuss about all three, how they basically help in improving the eye, and while designing you have to make a choice. Okay. So now we talked about increasing gain and all those things. So let's see how do we kind of, okay, if you look at an open loop system, you give an input and you give some output, and transfer function is basically, let's say, PBT dependent and there is no control at all. So you give some input, you give some output, you have no idea how much you got, and then it will be little unbounded problem. So to make this problem bounded, what you can do is basically, here you set a target. You set a target, okay, my target is, let's say, I am just for as an example, I am saying 100 millivolt. If my signal is more than 100 millivolt, I will say it's a error and I will go reduce the gain, and vice versa. If I get a 0, means my signal is less than the target, I go and increase the gain. So by this mechanism, if you see just a comparator, I have one comparator, and based on the output of this comparator, I can either increase the gain or decrease the gain. So this basically gives a flexibility to adapt the gain in case of there is a process variation and there is a change in this gain parameter. So this can be done in two ways. One is basically bang nature. Basically you don't know how much is this gain and all. You just look at if your output is greater than Vref, you decrease the swing, more than Vref, decrease the gain basically. Other way is basically dynamic. You first measure before you make any decision. Instead of static Vref, you instead of a static Vref which we talked about, you make a dynamic Vref. You vary this first to measure the incoming data and then you decide. You set a Vref target and you measure the incoming signal and then you decide. So it serves two purposes. One is here you are blind, how much is the swing. Here you have an idea how much is the swing. So that gives us flexibility. Basically, if you know your noise floor, then indirectly you can measure your SNR also. You know your noise floor is let's say 10 millivolt and this I measured this is to be 100 millivolt. You know what is the SNR floor we are dealing with. So that advantage comes, but it's little more complex. So next question I have, I'll answer this question in next foils. Every bit I'll do it or every 1000 bit, every 10,000 bit. So if I do it every bit, either I'll get this is a comparator, I'll get a increment or decrement. Means every bit I'll be changing the gain of this amplifier. Should I do every 1000 bit, 10,000 bit? Hold on to this question, I'll answer that later. Okay, so now this is the transmitter FFE or transmitter equalization. So what is done basically? What we saw, our problem is high frequency signal. When there is a high frequency or toggle, our swing get constant. So at that, whenever there is a toggle, I'll give little bit of extra swing, and if there is no toggle at all, I'll reduce the swing, thereby saving the power. And what is the impact? Look at the impact here. Basically, if you do not have this equalization mechanism or a 3-tap filter mechanism, this is how your transmitter output will look like at the receiver input. But if I have this, basically, what I did basically, I gave two negative coefficients and this is positive coefficients. You can see here, two negative coefficients and one positive coefficients. And I can adjust them depending on the channel I am dealing with, I can adjust them. And look at the swing I got basically. Whatever was not resolved fully, I had residual post cursors here, that got cancelled here. This is the concept of FIR from the transmitter. And the eye which was completely closed now opened up, but at the cost of swing. The important point to know, here swing got reduced, but eye got opened because we removed the noise. This probably I'll skip in the interest of time. This is basically one CML implementation and CMOS implementation is given. I'll just touch upon CMOS gives you the power benefit and CML gives you ease of implementation of FIR as well as the swing control. Because to control the swing, you just control this eye, you will get the swing control. And we'll see the next foil, how the equalization is so easy to control in CML implementation. So this is the cursor and these two could be your pre and post cursors. And your polarity can be here and you just control these tail currents to get the precursor and post cursor implemented. Whereas CMOS, that's not the case. For CMOS, you know CMOS always your swing is VCC. To control the swing, you must keep both these legs on to get a different swing other than VCC. What it says? To implement your swing control or equalization control through a CMOS circuit, you need to have a crowbar current flowing all the time. So the basic advantage of CMOS is basically gone. So there will be a crowbar current. So whatever power benefit we had, some of that benefit we will be losing here while implementing the equalization in through CMOS circuits. Okay, so let's look at the CTLE. Okay. So we saw we need to implement a high pass filter, means you introduce a 0, then pole. So if you, and then by moving the 0 to the left or by increasing the AC/DC gain, you can control the parameters to match your channel behavior. So that's basically the CTLE, and you can have a passive or active implementation depending on your area power appetite. So active comes with the benefit that it can provide you also a gain along with the equalization. It had other disadvantages. The advantage of CTLE is it cancels both precursor as well as the post cursor ISI. So we'll see in the next. The drawback is in this band, if there is any noise, it will amplify the noise also. It doesn't discriminate noise or the signal. It will amplify the noise and crosstalk also. And most, this is RC or active devices, your PBT variation will be huge. That needs to be tuned, which is not that trivial or easy basically. So let's look at passive implementation first before we go to active. Okay, so if you just a RC network basically, RNC. So assume that your frequency is 0, these two will be open circuit and this will be your gain, R2 divided by R1 plus R2 potential divider, and assume your frequency is infinity, your R component will go only, it will be C1 divided by C1 plus 2, again potential divider. So this is the DC gain, this is the very high frequency gain, and picking is basically high frequency gain by DC gain, and this is the equation. So what it says, by varying the R and C suitably, you can get your shape of the curve to mitigate the ISI. So there are no active devices, we are not dealing with any saturation, all those things. So of course it provides excellent linearity, that's why sometimes it is preferred over the active circuits. The drawback is it doesn't have any gain basically. So no gain, so that's obviously a drawback. So that if you are kind of want to combine gain in equalization, then your active stage is preferable. So if you look at here, it's just a amplifier, and then here you can see there are R and C connected, which makes this equation. And if you want to control the omega 0, the 0 location, if you have to control, you just vary this CS. And if you want to control the picking, this RS you control. So because this is the picking equation from this. And this kind of gives a glimpse how what happens when you control CS. CS you control, this moves, this entire curve moves to the left, but when you vary the R, you basically reduce the DC gain and get higher AC gain. Okay, so this is in one sentence, this is just amplifier with RC degeneration, and it's very sensitive because so many components are there. It's very sensitive to PBT, and tuning becomes a nightmare sometimes. When you have multi-stage CTLE, your tuning across PBT becomes a nightmare. Only 5 more minutes. Okay, I have to speed up a little bit. Okay, so now comes the DFE, which is basically discrete feedback FIR filter, which we have already seen. So basically you discretize the data and then apply a filter here to subtract portion of the incoming signal, because you know due to previous bit there was some ISI. So you are removing that portion through this, and if you look at the pulse response, this is how it will look like. The blue one is unequalized, and then the red one is basically after equalization. So of course here the advantage is this is a digital filter, we are discretizing then filtering. So noise and crosstalk will not be amplified. So this is an excellent way to remove your crosstalk and any noise amplification. Disadvantages is basically your precursor ISI cannot be cancelled, and you can see here it interferes with CDR operation because we are disturbing the edge. Hence, your CDR operation also gets impacted. This is one of the implementation. In the interest of time, I will skip this. Okay, now let's talk about LMS basics, which we already touched upon, but let's go into the little bit in details. So here we talked about we look at this output and then decide whether to increase or decrease the gain. So now, let's define few terms. So one is basically the error here. We are if your signal is more than the desired signal, we are calling it error is equal to 1. If it is less than, we are calling it error 0. And error equation, if I write desired data minus input into this gain. Input into this gain is this minus the desired signal is my error signal. And I am taking error square because this LMS stands for list of mean of square value. List of mean means average, square value. This is I am taking the square of this, and then and the third equation is basically I am saying my next coefficient or next gain will be now my present gain plus what is the step size I want to increase, whether its step size is 1 dB, 2 dB, whatever 0.5 dB, and whether I will increase or decrease. This delta tells me the direction, and this is says me how much I want to increase. This is the equation. Now, to get the slope, our basic mathematics, you would take the derivative of this and then find it out. I took the derivative with respect to W because we want to change the W. So basically, it becomes 2 into d minus Wx and minus x because we are derivative with respect to W. It basically into minus x, which is nothing but 2Ex because this is E, this is E. So, it is an important phenomenon for LMS. So, if you multiply this error with the incoming data, if you multiply these two signals, that gives you the direction. That is an interesting factor you can see. These two gives you the direction. If this 2 is positive, you have to increase, this 2 is negative, you have to reduce the gain. And this is the equation basically. And if you want to make it kind of bang or sine algorithm, that is also possible. So, what you do is you instead of E into x, you take sine of E and sine of x. You multiply the sine of E and sine of x, that becomes a sine or favorable for logic implementation, and this is the most widely used algorithm in HSIO domain. This is where I kind of promised to answer that question for every bit, or you want to do it in 1000 bit or 10,000 bits. So, if you do every bit, so means your logic has to implement, if you were dealing with 10 Gbps link, your logic also has to implement 10 gigahertz, which is practically not possible. The second problem is every bit you will be dithering whether it's increase or decrease, you must be making a decision. So, instead you take let us say 1000 bits and you basically ended up with 500 ones and 500 zeros. What you get it from it? So, basically you have reached your target, because of noise you are getting 500 ones and 500 zeros. Do not make any changes. Now, second scenario, you are getting 0 ones, all zeros, means you are running behind, you have to increase the gain basically. And if you are 600 ones and 400 zeros, just opposite, you are there but not reached this stage basically where you can say 50-50, basically average is 0, you have not reached the state where average is 0. So, here you have to decrease the gain. And here the I am saying 502 ones and 498 zeros. what you will do? Can I say it's almost equivalent to 500, 500 if I put little bit of threshold? If I put little bit of threshold, I don't want to have unnecessary toggles. This is almost same as 500 ones and 500 zeros. So I'll avoid, if I have a little bit of threshold, I'm saying hysteresis control, I'll probably hold it. So that is the basically implementation where you need to have a accumulator, you accumulate and then see how many ones and how many zeros you have and then decide whether to increment and decrement, and this gives you the step size, whether I'll increase in 1 dB or 2 dB and also and so forth. Okay, so this is an important table where gives a idea. So if you take data, impact of data on the error, that is basically your swing, and if you take the impact of previous data on the error, that becomes DFE. Same LMS equation can be used for VGA as well as DFE, and DFE of data or DFE of age can be used this way. So impact of, I am reiterating, impact of data on error is your gain, and impact of previous data on error is your ISI or DFE implementation basically. Okay, this probably will be my last point. So few concepts here basically. If you see initially when you adapt, let's say your gain is 0, you are quickly increasing and then this is the target. When you meet the target, this is where I was talking about 500 zeros, 501 you will get basically. You don't have to do anything. Once in a while you have to give just one toggle, both either positive or negative, and keep dithering around that. So you meet your target. And here an interesting thing, if your step size is really huge or latency is very high, so by the time you get the feedback that you have to decrease the gain, you have to overshoot already. So this is where the problem is. You have to avoid that. Your mu or the step size of the adaptation has to be really fine tuned so that you do not have undershoot, overshoot, and in that process you introduce a lot of error. So that's I think end of it, and then this is how it will be after the equalize. You equalize and then eventually, or I which was closed here at this input of receiver, at the input of sampler where I am discretizing, you will have an open eye again. So I think this was my last foil. Now I will invite Sriram to take it over from here, and we will take the question and answer if there is any at the end.
Yes. Yes, sure. Sure. Thanks, Ranjan. Yeah. So till now we have seen the overview, working and design of various SERDES blocks. Let us further analyze the SERDES system. So before analyzing the SERDES system, let us have a very brief review of a SERDES system. So we have seen that in the SERDES system, on the transmitter side, we have a transmit equalizer, and then we have a TX swing control which controls the power on the transmit side, right? Then the signal goes through the channel, and on the receiver side, the first block we had was CTLE, which is continuous time linear equalizer. This is an analog equalizer. Then we have a VGA which controls the power on the receiver side, and then we also have DFE, decision feedback equalizer. This kind of tries to remove the residual ISI that is present, and this is a discrete equalizer, right? Along with CTLE, VGA and DFE, we also have clock and data recovery circuit. What this is doing is, this is helping us to sample at the right point so that we can decide whether the bit is a +1 or a -1, right? So here we can see on the transmitter side, which Ranjan has already explained, the data looks to be pretty good and the eye looks to be pretty open, right? Because of the channel which contains the insertion loss, ISI, mismatches, crosstalk, reflections, right? The output of the channel looks to be completely corrupted and the eye is completely collapsed, right? So because of CTLE, VGA, DFE and CDR, all of them working together and nicely adapting at the input of the sampler, at this block, at the input of the sampler or the slicer, the data is recovered and we have a good eye height, right? And the data is very much recovered. Now let us look at the overall SERDES performance parameters. So in any communication system, what we generally look for is SNR, which is signal to noise ratio, and BR, which is bit error rate, right? Along with these two, what we have is eye height and eye width. So this is an example where on the receiver side, after equalization, right, this is the eye diagram, let's say. So here you can see that the eye looks to be pretty open, but this doesn't guarantee us we have a good eye height or eye width. Unless if CDR is sampling at the center of the eye, yes, we have a good eye height and eye width. But what if CDR is sampling towards the right side of this, right? Then what happens is the available eye height and eye width is significantly reduced, which in turn influences the overall SNR and bit error rate. So the point at which CDR samples plays an important role here in the overall SERDES system. And also here at the top, you can see the voltage noise. If the voltage noise is higher, what happens is the overall eye height is reduced. And in the x-axis, you can see that the time jitter. If this jitter is higher, then the eye width would be reduced. So voltage noise and also the time jitter plays an important role in the overall SERDES system, right? Also the analysis would be slightly complicated when you consider both voltage noise and timing jitter, right? Now let us look at what are the analysis methods that we have. In a SERDES system, we basically have three analysis methods. The first one is PDA, peak distortion analysis. Second one is analytical bit error rate, and third one is empirical bit error rate. Okay. So in PDA or the peak distortion analysis, what we do is we consider the channel that we want, which contains ISI, insertion loss, crosstalk, mismatches and reflections. Then we take a bit that we want to transmit and create the worst case scenario for that bit. And then we look at what kind of equalizer or the receiver we need to design. Right? This gives us a first cut analysis of how the system should look like. But this kind of worst case analysis may not occur in the real time. Okay? So let us look at the second method, which is analytical bit error rate. Here what we basically do is we assume the statistics or the PDFs of various noise and jitters, and then we analyze the eye height, eye width or eye diagram at each of the intermediate points in the receiver. Right? So this gives us a better analysis. However, this is still a mathematical model. Right? Then we go to empirical bit error rate, where you actually send n number of bits on the transmitter and see how many bits are coming into error. Right? Here, but the USB standard states the target bit error rate should be the order of 10 power minus 12, which means you need to send about 10 power 12 bits from the transmitter and see how many bits are coming into error. Right? And also this needs to be done some n number of times for statistical averaging. So this takes immense amount of time and which is not practical at all. So what we do is, you only transmit 10 power 5 or 10 power 6 bits, which is reasonable, and find the CDF or bit error rate and somehow find some kind of extrapolation algorithms. And do some kind of extrapolation and see what is the eye opening at the target bit error rate. Okay. So let us understand more on the CDF, PDF, what is this bit error rate, extrapolation algorithms in the further slides. So let us just brush up the concepts of PDF and CDF. PDF is basically probability distribution function, right? Here as an example, we took 3 Gaussian random variables with 3 sigmas. Okay. So basically what does a PDF say? It says that you pick up a value from this distribution, and it is saying mostly on an average I am going to pick up a 100 millivolt value, and the probability of picking up 130 or 140 millivolt or 60 millivolt or 70 millivolt is pretty less. That is what PDF is saying. And one more small comment is, as sigma is increasing, the width of the Gaussian curve is increasing. Okay. Then let us look at what is a cumulative distribution function. This is basically the area under the PDF from minus infinite to that point. So we know that the area under the PDF is plus 1. So the CDF value at a very large point would be 1 because the area under the PDF is 1, right. Now, the area, since this is a symmetric PDF which we took, the area under the PDF up to the mean would be 0.5, right. So, that is why the CDF value at mean of 100 millivolt is 0.5, okay. And this CDF is important for us in calculating the bit error rates, which we will see later. Now, one more small comment on CDFs is, see, the area under the PDF or the CDF at mean is 0.5, right. Now, if you move 1 sigma away from the mean, the area under the tail of the PDF or the CDF value is about 0.16. If you move 2 sigma away from the mean, the area under the tail is 0.023. Now, you move 7 sigma away from the mean, the area under the small tail of the PDF or the CDF is 10 power minus 12. This is an important result because USB standards target bit error rate is about 10 power minus 12. That is why 7 sigma and 10 power minus 12 we keep talking. Let us move further, and this CDFs will help us to calculate the bit error rate and I heights. Right? Now, before we go into the analysis, let us understand few questions. So, if you know sigma and if you know target bit error rate, okay, what should be the, can you estimate the I height? The second one is, if you let's say the I height is 0, right, then what should be the, can you estimate the bit error rate? And in this analysis, what will be the caveats or the pitfalls, right? And in the whole analysis of extrapolations, what should be the sample size taken and what kind of samples needs to be taken to do some kind of curve fitting, right? This we'll go through. So, let us take a simple problem of bit error rate estimation in Gaussian noise. So, on the transmitter side, I want to transmit +1 or -1, let us say with 100 millivolt and -100 millivolt. On the receiver side, Gaussian noise is added. Then what happens? The PDF looks something like this, right? Around 100 millivolt, we have a Gaussian PDF, and -100 millivolt, we have a Gaussian PDF. Now, if the noise is so high such that the 100 millivolt is going on the negative side, then the positive bit +1 may be detected as -1, which is bit error. Similarly, a -1 is added with a lot of noise such that it is going on the right side, and that can also cause a bit error, right. Now, basically bit error rate is what? The area under this PDF, from -infinite to 0, and the bit error rate for the negative symbol is area under the PDF from +infinite to 0, right. So, that is why the areas under the PDFs is basically CDF. So, that is why we have drawn a CDF here. And here let us zoom into this region around 0. So, we see that around 0 the bit error rate is about 10 power minus 7, right, which means if you send 10 power 7 bits, 1 bit is going into error, right. Here note that the sigma we have taken is 20 millivolt. Let us see what happens if sigma is reduced to 14 millivolt. So, as we know, if sigma is reduced, then the width of the Gaussian curve reduces, right. So, when you take the CDF, definitely the tail region has reduced. So, the area under the tail region for calculating the bit error rate is reduced. So, ultimately the bit error rate at 0, the CDF at 0 or the bit error rate is 10 power minus 12, which means you are sending 10 power 12 bits and only 1 bit is going into error. So, as sigma is reducing, bit error rate improves. Intuitively also it makes sense. And other way to improve bit error rate is, instead of sending with 100 millivolt, send with 150 millivolt and -1 with -150 millivolt, which means increasing the transmit power, right. Definitely the both PDFs will move further away and the tail area under the tail of the PDF will reduce. So, bit error rate will improve, but this is not possible because transmit power is constrained. Let us understand what is the I height margin or the I height, right. So, again in this example, take a PDF, draw a CDF from the PDF, which means area under the tail distribution of the PDF, and zoom in this region, and on the y axis see where the value of the CDF is about 10 power minus 12. On the x axis you can see that it is about positive side 15 millivolt and negative side minus 15 millivolt. So we have an average of 30 millivolt eye height margin in this case. Right. Now let us understand what are these bathtub plots. These are basically to improve the resolution of the PDF curves. Why do we use it also, we will see. So we now understood that we need to look at PDF, then we need to go to CDF. In CDF you can see that around the mean of 100 millivolt, the curve looks to be pretty linear, right, and it has a good resolution. But what we are interested in is the tail of the PDF or the tail of the CDF, and the resolution at this point is pretty bad. So what we do is we take log of the CDF so that the resolution has improved significantly. That is why we use these bathtub plots, right. So bathtub plots are basically taking log of the CDF. Now let us take an example where on the receiver side after equalization there is some residual ISI left because CTLE and DFE could not remove some part of ISI. That is why we have two humps there, or the deterministic noise, and the tail part of this PDF is due to the Gaussian random noise, right. From this PDF calculate the CDF, right, from the actual data that we received, calculate the CDF, which is the red portion, and then do some kind of extrapolation and look at the eye opening at the target bit error rate. Now let us look at what is this extrapolation algorithm. See, for this we use something called as Q scale. So basically Q scale is a linearized version of the CDF or the bathtub curves. So it reduces the tail fit method to a linear regression problem. So basically Q scale is square root of 2 inverse of error function 2 times bit error rate, right. So basically what it is trying to do is, you have the, so in the previous slide, see at the center portion it is due to the deterministic noise and the tail portion is due to the Gaussian noise, right. One of the key mathematical result that we can derive easily is, if the random variable is Gaussian, then the Q scale comes out to be linear, okay. Since in the previous diagram we saw initial portion is due to deterministic noise, you draw Q scale, it may not be linear, right, but the tail of the distribution, sorry, and that the tail part is due to Gaussian random variable, so the tail would be definitely linear. So since it is linear, you can take the samples corresponding to this linear portion and extrapolate it using linear regression, which would be very easy, right. Then you can look at what is the eye height at the corresponding target bit error rate of 10 power minus 12 or 7 sigma, right. So this is how you kind of extrapolate and get what is the eye height at target bit error rates. Now in this extrapolation we may come across some extrapolation errors. What happens if you are extrapolating based on the deterministic noise, right. See here, if you are extrapolating the red color points which are corresponding to deterministic noise, then the eye height estimated is almost 0. This is kind of an overestimation problem, right. So you need to take the samples corresponding to the tail of the distribution which is purely Gaussian and then extrapolate it. So you will have a correct eye height estimation at the target bit error rate, right. Okay. This is a simple formula of eye height calculation, which is equal to deterministic noise plus random noise peak to peak, and any random noise peak to peak is a function of target bit error rate. In this case the target bit error rate is 10 power minus 12, so Q scale value would be 14. So deterministic noise plus 14 times the sigma. Similarly for minimum eye width it is data jitter plus random jitter peak to peak, which is data jitter plus 14 times sigma of the jitter. Now let us look at the SERDES architecture case study. So what we have done is we have modeled all these blocks in Simulink and MATLAB, and we wanted to look at how is the system behavior. So here we have taken TXFFE, which is a 3-tap filter, and this is dictated by the protocol, and we also took channel loss or the insertion loss to be 24 dB as worst case and 5 dB as the best case. These are the limits defined by the standard. And then we have also designed CTLE, which is an analog filter with boost from 0 to 15 dB at Nyquist frequency. And then we designed AGC, which is having a gain from minus 10 dB to 4 dB, and this is a simple low pass filter which only gives us some kind of DC gain. Then we also designed a DFE, which is a 4-tap discrete equalizer. So this basically tries to remove any residual ISI without amplifying any noise, right? And then we also designed this CDR so that the data is sampled at the right points. Now let us look at the results and analysis. So here on the left side you can see that the channel loss is about 24 dB at 5 gigahertz, and the transmit side and receive side resistance we have taken as 50 ohm, and transmit side and receiver side capacitance we have taken as 1.1 and 1 picofarad, right. On the right side bottom we can see that initially the data is completely corrupted, right. After that, because of CTLE, DFE and VGA and CDR adapting nicely, what happened is I is slowly opening up, and at the end we can see that the data is pretty much cleared, and we can easily distinguish between +1 and -1. And the above diagram, data histogram, is showing is kind of a PDF or a data histogram for this below data, right. In the above you can see the CTLE is nicely adapting and it settled to 15 dB boost. Similarly, VGA has adapted parallelly to -4 dB, and the DFE taps are also settled. In the left side, you can see that the actual thick lines of red and blue are corresponding to the CDF or the bit CDF of the actual data. Then from the Q scale that we discussed earlier, we are extrapolating this whole curve to find what is the eye height at the target bit error rate of 10 power minus 12. So in this case we are having a good eye height of about 75 millivolt, right. Now let us look at the other case where it is a short channel. We have about 5 dB of channel loss, right. In this scenario also initially the data looks to be corrupted, but as the CTLE, VGA, DFE and CDR adapts, the eye has opened pretty much and we have a good high opening, right. In the above you can see that CTLE has settled very fast and it is toggling around 4 dB boost, right. And similarly VGA and DFE coefficients are settled. Here after the extrapolation using the Q scale that we saw earlier, we have about 110 millivolt, which is very good. Now let us look at all the key takeaways of this SERDES discussion that we have. Okay. So due to increased data rates, ISI and other complexities, the wireline data transfer is no longer just a circuit problem. It is not just building circuit and seeing how is the performance, right. So we need to adapt the techniques from wireless communication to wired communication as well, and some kind of advanced adaptive equalization techniques from DSP needs to be taken into wireline communication, right. And also statistical link analysis should be used for estimating the errors, right? And here multi-level PAM, which means here we have shown only BPSK, we can use higher PAMs to improve the data rates, right? Also error encoding and error correction schemes can be used so that you have a better bit error rates, right? And along with that we need to model the end-to-end system as accurately as possible, which means the transmitter, channel and the receiver needs to be modeled as accurately as possible. And in channel you need to model insertion loss, ISI, crosstalk, mismatches, reflections, right, so that the model performance also is on par with what we see on the real chip. Then we also need to model this noise and jitter at different points in the receiver, right, so that the results that we get in the simulation will be same as what we get in the real circuit, right. And actual circuits can have a lot of non-idealities such as non-linearities or DC offset or frequency dependent parameters or some kind of leakage currents or any kind of residual errors. So all of these also needs to be modeled, right? And the real circuit also can have PVT variations, which means process voltage and temperature varying parameters. So these are also needs to be taken in our model. So ultimately along with all of this, unless the CTLE, VGA, DFE and CDR doesn't work together and adapt well, the system overall performance will not be good, right? Yeah. So with this we tried to cover the overall SERDES system. Yeah, and we are happy to take some questions.
Thank you, Ranjan and Sriram. That was a fantastic session. So we can take a couple of questions.
Thanks, Ranjan. It's a detailed presentation. So, as we know that the problems are channel, noise, and ISI. So, in your point, what are the chances of transmitting digitally to avoid all the problems? So, I have a transmitter, analog data, I convert into digital, then I transfer the digital data to the channel, then I convert again the digital data to analog and then process it. So in future we see any digital techniques for the SERDES system, or still we need to stick to only analog?
Okay, so see the concept we discussed is digital communication only. See, when you say digital, it's 1 0, right? It's 1 0, but we have to assign some voltage level, and that gets distorted due to channel loss. So when you say digital communication, can you elaborate a little more? What do you mean by digital communication?
Transferring the data digitally.
This is digital. What you are transmitting digital.
So can we see entire digital systems?
The inverter to inverter communication.
Yeah.
No, because of channel, the digital signal itself will become an analog signal.
Yeah, that is there. So the channel is problem, right?
But what I can say, or people do also, when speed goes, let's say, beyond 64 Gbps, instead of an analog equalizer, people go for digital equalizer. So in the distorted signal they sample, then equalize in digital domain. All the equalization techniques we demonstrated is analog implementations. For complex circuits, they convert the signal to digital, sample and convert to digital. Equalization happens in digital, that is little more power hungry.
Okay.
People do that.
Okay. So is there any chance to improve the channels? So the channel is the culprit, obviously. Yes. So why can't the industry people are improving the not improving the channel?
Cost. the basically, wherever your cost is minimum, you will take that approach. So now if you make a platform in gold, probably possible, but who will buy it? That's number one. Number two is, it's not that they are not improving. Look at the PCI Gen 4, which was 16 Gbps, channel loss was 28, and at 32 Gbps, your channel loss was 31. So double the speed, only 3 dB extra. So means channel, they also improved a lot. But beyond that, your cost will be impacted.
Okay, thank you. Thank you so much.
Thank you.
Hello. So thank you for the nice presentation. So
You can sit down.
Yeah. So you discussed that the DFE also impacts the CDR performance. So is there any limit on the number of taps in the DFE, or what is the compromise we need to do in terms of the CDR performance not degrading drastically when we are implementing the DFE part?
There will be impact, but what is done is when you go higher and higher speed, your age is also equalized. So age also you equalize, and age also, now there will be no ISI on age, so that your impact will be minimized.
So any limitation on the number of taps versus CDR performance?
No, there is no limitation on number of taps. Number of taps depends on the how much ISI you have, how much long tail you have. Based on that you decide the number of taps, and large number of taps comes with the disadvantage is that the more number of taps, more number of dithering jitter also, because each tap will be dithering will be introducing some noise. It could be 1 millivolt or even 0.5 millivolt. If you have 30, then there will be a probability of how many of them toggling together. That will add into the noise. So that will be a disadvantage. On CDR, no, there is no.
Thank you. Thank you very much.
Thank you.
So in interest of time, we won't be taking any further questions, but Ranjan and Sriram will be available. You can chat with them during the lunch time. So on behalf of the organizing committee, we would like to felicitate our speakers with a small token of our appreciation. So we will be starting the next session at sharp 2 p.m. Please be in the room by 1:50. And the next two sessions here will be on formal verification and advanced verification techniques. Thank you.